I'm Jeff Grove, and this is Partial Differential Equations. Today, we're going to talk about the two-dimensional wave and heat equations. To this point, we've done a pretty good analysis of a vibrating string, but more than just strings vibrate. You could have an entire membrane like the head of a drum. We're going to begin with the simplest possible cases, however. We'll look at what happens in rectangular coordinates, reserving a circular drum for later. We'll begin by looking at the wave equation in two dimensions. If we have x, y, and u coordinates, we'll be working above a little rectangular patch in the xy plane. Undulations of the membrane will be a surface that lies above the rectangular patch. The rectangle will be given by a is less than or equal to x is less than or equal to b, c is less than or equal to y is less than or equal to d, and of course t will be non-negative. To make things simple, let's suppose that the rectangular patch is centered at the origin. Also, we need both initial and boundary data. So the boundary data, or the boundary condition, same thing, will be that u, restricted to the boundary of the region, will be 0. No displacement at the edge of the drum, if you will. In this case, a rectangular drum. This condition must hold for all t. In addition to the boundary data, because we have two time derivatives here in the differential equation, we need two initial conditions as well. So the initial displacement will be some given function. X, little vector over the top, will allow for both x and y coordinates. But this gives us the initial displacement of the membrane, but not the initial velocity. For that, we'll define u naught dot at x, allowing for the velocity to be described at each point at time t equals 0. We'll try a similar trick to what we've done before. We'll assume that the solution is separable. And in particular, that means that u can be expressed as a function of x alone times a function of y alone times a function of t alone. Plugging this into the differential equation gives 1 over c squared big X big Y t dot dot equals x prime prime yt plus x y prime prime t, where the prime on the x refers to a derivative with respect to the x variable, whereas a prime on the y represents a derivative with respect to the y variable. So these are different derivatives. Dots, of course, represent derivatives with respect to the time variable. Dividing through by x, y, t, we obtain 1 over c squared t dot dot over t equals x prime prime over x plus y prime prime over y. Now we need to figure out what the consequences are to these separated variables. Clearly, the left-hand side depends only on the variable t. The right-hand side depends upon both x and y. Since the right-hand side does not depend upon t, whereas the left-hand side does, we deduce that we get some kind of a constant. By trichotomy again, we have three choices. This could be positive, negative, or 0, and we need to explore all three possibilities. If lambda is positive, then t behaves either like an exponential growth or an exponential decay factor, neither of which is appropriate for a frictionless membrane. So, you can see for physical reasons, this cannot be positive. Similarly, if lambda is 0, that means that t must grow linearly or be constant. Neither of those is appropriate either. We can see then the only real possibility is for lambda to be negative. And that's why instead of writing this as just lambda, let's write this as minus lambda squared, emphasizing that a negative is physically appropriate in this case. Under these conditions, we get t dot dot plus c squared lambda squared t equals 0, which has the solution c1 cosine of c lambda t plus c2 sine c lambda t, allowing for an oscillating membrane. Now that we see that the right-hand side is minus lambda squared and we have a solution for t, we need to figure out solutions for both x and y. So we'll move this term over and we'll see that now we have these variables x and y separated, so that the left-hand side is a function of little x, the right-hand side is a function only of little y. These both must be equal to a constant again. That constant could be positive, negative, or 0 by trichotomy, of course. You'll see then, by a simple analysis, that this must be a negative. Otherwise, x will grow exponentially or decay exponentially. And again, for a frictionless membrane, it has to oscillate forever. So neither of those are appropriate. We deduce then that x prime prime over x is minus mu squared for some constant mu. We have then x prime prime over x is minus mu squared. But the next equation, moving this over here and that over there, gives y prime prime over big Y is mu squared minus lambda squared. Again, for the same reasons as before, we require this to be a negative constant. Let's say negative nu squared. Let's say then that t is b1 cosine of lambda ct plus b2 sine of lambda ct. X is going to be c1 cosine of mu x plus c2 sine of mu x, and y is d1 cosine of nu y plus d2 sine of nu y. We now need to know how to choose mu, nu, and lambda so that we can satisfy the boundary conditions. How do the boundary conditions come into this? Well, we have to be 0 at the boundaries. If u at all x on the boundary for all time is 0, then at x equals 0 and y equals 0, both x and y must be 0. The only way that can happen is if C1 is 0 and D1 is also 0. To obtain zero displacement on the other two sides of the rectangle, we must have x of A equal 0 and y of B equals 0. So we'll have C2 times the sine of mu A must be 0. Assuming that C2 is not 0 and we don't have uniformly 0 displacement, we'll have mu equal to n pi divided by A, where n is an element of the set of integers. We'll also have d2 sine of nu B equals 0, which implies then that nu is m pi over B, where m is also an element of the set of integers. Because of symmetries, we can allow these to be an element of the set of natural numbers. Note also that lambda squared is mu squared plus nu squared. And if mu and nu take these forms, that gives us a formula for lambda as well. Since these mu's and nu's will depend upon the integers n and m, we can give them little subscripts. Lambda will have two subscripts, m and n, and it's going to be the square root of n pi over A squared plus m pi over B squared, and we'll give this the principal square root, since the lambdas may be assumed to be positive. Factoring a pi squared out of the square root, we'll have pi times the square root of n squared over A squared plus m squared over B squared. We'll have u is the sum as m and n go from 1 to infinity. This is really two sums here. The sum as m goes from 1 to infinity, and the sum as n goes from 1 to infinity separately. We'll have b mn1 cosine of lambda mn c t plus b hat mn sine lambda mn ct times, we still have to multiply by the sine of n pi over a x times also the sine of m pi over b y. So solutions that look like this also need to satisfy the initial conditions, and so we need to check those next. Notice that u, evaluated at x and y, but at t equals 0, gets rid of the b hats and leaves only these b's. And we know these go from 1 to infinity, so we'll just leave that part off. We'll have b mn cosine at 0 is 1, so we're just left with the sine of n pi over ax, the sine of m pi over b y. Now, we also have the initial condition that this has to satisfy. It has to be equal to some function u0 of x. What is an appropriate Fourier basis in this case? What is the Fourier basis? Well, turns out we can use the sine of n pi over a times the sine of m pi over, and this is x, m pi over b y. as our Fourier basis. Will these be linearly independent and will they be orthogonal? And the answer is yes, provided the point nm is not the same as the point n prime m prime. If you choose different values of n and m for two different elements of this set, you'll get something that is orthogonal. What is more, if you take the inner product of one of these with itself, you'll have AB over 4 as the value of the inner product. The integral will, of course, in this case, be a double integral, since we're integrating over the entire rectangle. It follows immediately, then, that the coefficients b, m, n are going to be given by the following. We'll normalize by multiplying by 4 over AB. We'll integrate over the entire rectangle the initial data times our Fourier basis elements. This allows us to deal then with the initial displacements. The initial velocities will come into the determination of the b hat mn's. If you take the derivative of the representation of u that we had, you'll get the sum as m and n go from 1 to infinity. The b m n's times minus lambda m n c sine lambda m n c t plus b hat mn lambda mnc cosine lambda mnct, all times the sine of n pi over ax sine m pi over by. Evaluating at time t equals 0, we'll have u naught dot of x equal to, this part goes away, this is 1, we'll have the sum on m and n of the b hat mn's lambda mnc, this is 1, sine n pi over ax sine m pi over by. We can find a Fourier representation of the u naught dots, the initial velocities for the initial displacement, but then we equate coefficients to figure out the b hats. We'll have to divide the lambda mn c's off by taking inner products on each side with respect to elements of the Fourier basis. We can solve for b m n hat. It will, of course, be 4 divided by AB. We'll have the lambda mnC's divided off. And then the integral from 0 to a, the integral from 0 to b of u naught dot xy times elements of the Fourier basis. Sine of n pi over ax, sine of m pi over by, and dy dx. Let's look at an example of a square drum. We'll assume that all of the initial velocity coefficients are 0, so it is not moving initially, but it is initially displaced. We'll choose some of the BMNs to be not 0, and we'll look at different values that we choose and see what happens to the drum and how it vibrates with different values of these B's not 0. We're going to animate the drum. with various cases. Let's suppose A is 1 and B is also 1. Let's suppose that C is 1. Let's take lambda 1, 2. Now, remember that was pi times the square root of n squared over a squared plus m squared over b squared. Let's choose n to be 1 and m to be 2. So this will be the square root of 5, 1 n squared plus m squared, since a and b are both 1. Let's define our function u that maps x, y, and t onto, let's see, what did we have? Cosine of lambda 1, 2 times c times t. C is 1, so we don't need to put that in there, times the sine of, let's see, we had n times pi divided by 1 times x times the sine of m times pi times y, and with plots we need to animate in 3 dimensions our function u of x comma y comma t, where x goes from 0 to 1, y also goes from 0 to 1, and let's suppose t goes from 0 to 2 divided by the square root of 5. So here's our graph. The drum displaced by 0 at the sides. It's initially displaced in this way, and as time goes by, it oscillates in this fashion. This was the drum where we chose all of the coefficients to be 0 except for b 1, 2, where n was 1 and m was 2. Okay, so let's stop that. Let's change the coefficients that are going to be 0 or non-zero. Let's suppose that instead of m equals 2, we choose m equals 3 and n equals 2. What does that do to our function? You can see we'll have a few bumps here and a couple bumps this way. If we click on this, I want to repeat this. Let's see, do we have this in the right? Oh, we had square root of 5. It's not going to be square root of 5 anymore. It is going to be the square root of, what is it, 4 plus 9, square root of 13. I want this to be able to repeat. And you can see how the membrane vibrates when we choose these particular oscillatory modes. We can combine these oscillatory modes, or we can have separate oscillatory modes by just choosing only one coefficient to be non-zero, which is what we've done. Which coefficient you choose to be non-zero determines how many little bumps you get on the membrane. So you can change this from n equals 2 and m equals 3 to any choice that you'd like. You can combine multiple terms if you'd want with different coefficients. I just chose the coefficients to be 1 for sake of simplicity. The time that you choose will have to depend upon which m and which n that you are working with. We've solved now the two-dimensional wave equation on a rectangle. How would you do the same for the heat equation? It's pretty easy to see what you would get in this case. you'll have u be the sum on m and n again as we go from 1 to infinity. In this case, you only get one initial condition. Bmn will be the coefficients that you get as a consequence, minus e to the minus c lambda mn squared t times the sine of n pi over ax, the sine of m pi over by. Here, just as before, lambda nn is going to be pi times the square root of n squared over a squared plus m squared over b squared. Also, we're assuming that the boundary data are all 0, and that explains why this decays away to 0 as t goes to infinity. In addition, just as before, the bmn's are going to be 4 over ab, the integral from 0 to a, integral from 0 to b of the initial displacement times these Fourier basis functions. Sine n pi over ax, sine m pi over by, dy dx.